So today we look at section 6.5, which covers the Central Limit Theorem, which is a very important theorem in statistics. So before we get started on that, just to recall from the last section, we looked at the distribution of these x bar values, right? Where x bar was the sample mean length of 5 trout. So we were thinking about if we took all of these sample means, these mean values of 5 trout, and we lined all of those up on a number line, what would those look like? So before we actually talk about the central limit theorem, we're going to talk about another theorem. This one isn't as well known. In fact, it doesn't have really a name. It's just theorem 6.1, but it'll get us started. So this is a theorem that involves working with a normal distribution. So we're working with a normal distribution already. So we let x be a random variable. Could be anything, but it's a random variable with a normal distribution. It has a mean mu and a standard deviation sigma. And we're going to let x bar be the sample mean corresponding to random samples of size n, right? So just to think about what we did before we had a sample mean corresponding to random samples of size 5, right? That was the trout example. But this is just more generally speaking. So x bar is a sample mean corresponding to random samples of size n taken from this x distribution, right? X is the random variable. Could be anything. Could be the length of a trout. Could be the snowfall in Grand Rapids in January. Could be anything. But in this case, if we are taking these samples from a normal distribution, then the following are true. The x bar distribution is a normal distribution. So what this means is that if we are taking these samples, these x bar, these samples from a normal distribution, and then we line up all of these sample means on a number line, if we were to line them all up like a dot, like a dot plot, they would form a normal curve also. So what this says is if we're sampling from a normal distribution, so we're taking these sample means from a normal distribution, then the x bar distribution is also going to be a normal distribution. And the mean of the x bar distribution is the same as the mean from the x distribution. So if you remember the example from 6.4, the x distribution was the distribution of lengths of trout in the entire pond, right? So we had this x distribution, and this was the length of all the trout in the entire pond. So this would be thousands of numbers. Each number corresponds to the length of a trout. And then we kept taking samples of size 5, and we would get the sample mean of like 10.2. And then if we kept taking these samples of size 5 and kept getting these different means, then the collection of all of these sample means was our x bar distribution, right? So what this is saying is that if this x distribution is a bell-shaped curve or is a normal distribution, then this distribution will also be a normal distribution. So when we line up all these x bars, all these values, we're going to get another normal distribution. And it says that the mean of this x bar distribution is the same as the mean of this distribution. Now, if you remember what we talked about in 6.4, we said the standard deviation of the x bar distribution will be smaller. Because remember, we were talking about the fact that occasionally a kid would catch a 14-inch trout, but it would be extremely unusual to find the mean of 14 inches, because that means that kid got really lucky and caught the 5 of the largest trout in the pond. So we said that when you line up all these x bar values, this sampling distribution, the distribution of these samples, the sample means would be it'd be like a taller, skinnier bell-shaped curve. So they're going to be a smaller standard deviation. So there's less variation here because all the large or the small samples that were here would get averaged out here because we're averaging them out with other values. So you can see right here, so this x distribution has a standard deviation of sigma. Well, the x bar distribution, you take sigma and you divide it. So if you take a number and you divide it by something, it's going to get smaller, right? And again, we're dividing it by square root of n, so it's going to be a number bigger than 1. So if you take a number and divide it by another number bigger than 1, it's going to get smaller. So the formula for the standard deviation of this x bar distribution is right here. Okay, so the note here is this. This is important for this part. When x has a normal distribution, x bar also has a normal distribution, and it doesn't matter what the sample size is. So the reason this isn't really a well-known theorem is because this isn't all that helpful. Like, if we know we have a normal distribution, we can just start using all the stuff from chapter 6 to evaluate this distribution. So we don't really need to do this to take these samples here. What we'll see is important is if we don't know about this, or maybe we know x is not normal, using what we'll see later, the central limit theorem, will allow us to still get a normal distribution with the x bar values. So if we have a normal distribution of these values, we can use all the chapter 6 techniques that we've learned, and there are many others that we don't cover because this normal distribution has been studied for a long time, and then we'll see that we can use that on the x bar distribution and infer back to the original distribution even though it's not a normal distribution. So that'll be important for later, but for now this theorem 6.1 isn't super helpful because it just basically says if we are sampling from a normal distribution, well, then our sampling distribution will be normal regardless of sample size. Okay, and then there's another note here. We can convert the x bar distribution to the standard normal z distribution. So in other words, we can still use these z-scores using these formulas listed here. So let's take a look at these. So this one's pretty easy. It just says the mean of the x bar distribution, which means the mean of the sampling distribution, right? It's a distribution of these samples, is the same as the mean from the x distribution. And here we've got a formula for the standard deviation of our sampling distribution. We just have to divide the standard deviation of the x distribution by the square root of n. And what is n? Sample size. And then we've got a new formula for our z-score, and this we have to be a little bit careful about. So it's basically saying, I mean, it looks kind of similar here, but here's what we had before. Let me put the old one. We had this. X minus mu over sigma. This is what we used before, but now we're going to change this a little bit. So we don't have x, we have x bar, and we have the mean of the sampling distribution, and then we divide it by the standard deviation of the sampling distribution. And this version of the formula is just substituting this for its formula right here, right? So this is the one we'll normally see, and here's what we have to be careful about. Order of operations is going to give you the wrong answer if you're not careful. So this gives us all kinds of trouble for two reasons. Number one, we need to use order of operations, so it's best if you just put parentheses here every time. And the other thing is, look at what this says, divide. Something about this, I don't know why, but students all the time just multiply or they forget about the divide, but we have to realize that's a divide, right? It says divide. And that's why order of operations can get screwed up if you're not careful. So make sure you put these in parentheses or do something else just to make sure that you don't just plug. If you just go x minus mu divided by, it's going to just divide by the mu, right? So we have to be really careful with the order of operations here. So just put parentheses here. That way it'll work every single time. Just make sure you hit divide. So this is from section 6.2 when we just had one individual raw data point, 6.2. 6.5, we don't have one data point, we have the mean of n of them, right? So it's different. So when we have one data point, we use this. When we have a sample mean, we use this one here. Okay, and then the standard error, I don't really use this phrase very often or ever, but the book does, and a lot of computer printouts do. The standard error, it's nothing fancy, it's just the standard deviation of a sampling distribution. So sampling distribution is what we're studying right now, X bar. So the standard error is just this thing. This thing right here is called the standard error. So this expression will often appear in statistical software printouts. They'll say the standard error is this. All they mean is this, standard deviation of the sampling distribution. That's the standard error. So to see how this works, you've got an example here. This is example 12 on page 321. And it's still talking about the trout pond. So it says, let X represent the length of a single trout taken from the pond. So X is our random variable, right? Just represents the length of a single trout taken from the pond. It is known that X has a normal distribution, which that's key right here. It is known that X has a normal distribution. If we know that, then we know for sure that X bar, if we take samples out of here and we line up those samples, so we take the mean of all those samples, that would be our X bar distribution. It's definitely going to be normal, right? So if X has a normal distribution, X bar will also have a normal distribution for sure. So it tells us that this X distribution has a mean of 10.2 inches and a standard deviation of 1.4 inches. And then part A, so we've got kind of a big gap here. Part A says, what is the probability that a single trout taken at random from the pond is between 8 and 12 inches long? So I just moved this down a little bit and rewrote this so we had this information up here. So we are sampling from a normal distribution, right? We're sampling from a bell-shaped curve. So if we take the mean of these samples and line them up on a number line, we'll get another bell-shaped curve because our X bar distribution will be normal from theorem 6.1. So this is a really good example to see the difference between a single trout and more than one trout. So this says, what is the probability that a single trout taken at random from the pond is between 8 and 12 inches? Well, the key here is it's a single trout. This means we are just using section 6.3 material. It's a single trout, so we're going to use this. Right, because this X represents one data point, a single trout, so we would use this. And they're basically, when they ask us this, the probability, here's what they're asking us. What's the probability that this trout is between 8 and 12 inches for this trout? Right, this is what they're asking us. So what we want to do is convert it to a z-score, always, right? We always want to convert these to z-scores. So we're going to rewrite the question, but we want to use z instead of x. So we're not using x values, we're using z-scores. So we just need to see what z-score does an 8-inch trout correspond to and what z-score does a 12-inch trout correspond to. And we can use this formula for that. So for the 8-inch trout, we would go z equals 8 minus 10.2 over 1.4. And I'm just getting these, they were listed above, right? The mean set is 10.2, standard deviation is 1.4. And remember, be a little careful with the order of operations. So I cannot just go 8 minus 10.2 divided by, because it's going to divide just this, right? So I need to go 8 minus 10.2, enter, get that value, then divide by 1.4. And if you do that, you will get right around, well, first, is it going to be positive or negative? Without thinking about the math. It's got to be negative z-score, right? Because 8 is below the mean. 12, on the other hand, is above the mean, so that would be a positive z-score. And sure enough, you get right around negative 1.57 for this one. And then if I do the same thing with 12, I get 12 minus 10.2 over 1.4, which ends up being 1.29. So you get negative 1.57 for 8, 1.29 for 12. And then to figure this out, we go to our calculator, normal CDF, negative 1.57, 1.29. And that will give us roughly 0.8433. So what that's saying is, what is the probability that a single trout taken at random from the pond is between 8 and 12 inches? Pretty good chance of that, about an 84% chance, right? About an 84% chance of that happening. And this is nothing new here. We already know how to do this. This is a section 6.3 question. But now they're going to ask something else. Now they're going to say, what's the probability that the mean length of 5 trout taken at random is between 8 and 12 inches? So the big difference here is we don't have a single trout. Now we have 5 trout. It's a mean length X bar of 5 trout. So now this is section 6.5. We have our new z-score formula. Remember, there's things we have to remember. 1, make sure you use order of operations correctly. And number 2, remember that's a divide. We have to divide there. So the question will look kind of the same when I start with this probability. I'm going to write it incorrectly first. Let's see if you guys can see what's wrong. So this is really close, but it's not quite right. So this right here is for an individual x. We need the mean length x bar. So I just need to add a bar there. Right, so these two look the same, but this is the probability of an individual trout. This is the probability of the mean length of 5 trout. So we do the same thing as before, though. We want to convert it to a z-score. So we're going to do that like we did before. But this time we have our new formula. So for the 8, we would do it like this. So we would go 8 minus 10.2 divided by, and then this time we have 1.4 divided by the square root of n, right? Square root of n. N is the sample size, so 5 trout, 5, n is 5, so it's divided by the square root of 5. And again, just be careful here. This would be a good practice one. So whatever you do, don't wait for me to get the answer. Calculate it first and make sure you get the same answer that I'm going to get. So if everything went right, what we should get here is negative 3.51. So if you got something different, remember we need to subtract this, and then, if you put it in parentheses, it'll work out for sure. So we subtract this, and then down here, when we divide it, it's 1.4 divided by the square root of 5. And then if you do that, you should get negative 3.51. And then we've got the other one for the 12. So 12 minus 10.2 divided by 1.4 divided by the square root of 5. I'm just going to use a different color here again just to emphasize, because I know this gives us trouble. And this gives us 2.87. So when we put these over here, we have negative 3.51, 2.87. Now these z-scores seem a little more extreme than these, right? This is basically saying the z-score for this 8-inch trout is negative 1.57. So we know because it's negative, it's below average. And this is, roughly 1.5 standard deviations below the mean, right? Z-score of negative 1.57, not all that unusual. Remember what an outlier is. Where most people define an outlier is 2.5 standard deviations, either above or below the mean. So neither of these are outliers, right? They're both fairly common, right? About 1.5 standard deviations below the mean, a little more than 1 standard deviation above the mean, fairly common. Now you look at these, and now these are not very common. Negative 3.51 is not common at all, right? So basically they're saying it would be unusual to get a mean length of 8 with 5 trout are taken, because 8 is a shorter trout. It's a small trout. So while it wouldn't be unusual really to get one of them, it would be unusual to get a mean length of 5 of them to be 8, because that means that all the trout probably would have to be pretty small to get a mean of 8. And that's not all that likely based on the z-score. And then same thing with a 12. You can look up here and see, well, a 12-inch trout has a z-score of 1.29. It's, bigger than average, but it's not all that unusual. But it is more unusual to get a mean of 12. So that means that if this kid had a mean length of 12, he was unusually lucky, right? He had just a bunch of the bigger trout in the pond. So much so that it would be considered an outlier, right? 2.87 z-score. So it's not all going to be all that likely to happen. So when we figure these out, you can kind of see, if you just think about what this is asking, if you go under the standard normal curve, because remember this is standardized now, these are z-scores, between negative 3.51 and 2.87, you're going to have a lot of that curve underneath here. This is going to be close to 1, right? It's going to definitely be bigger than 0.8433. So we head to the calculator, see what the calculator says. Negative 3.51, 2.87, and you should get 0.9977 or something very close to that. So this means that the probability that the mean length of 5 trout taken at random is between 8 and 12 inches is more than 99%, right? Roughly 99.8% chance of that happening. So it's a lot more likely that the mean of 5 trout would be in this interval. So then there's a question here, why are these probabilities so different? In other words, one of the probabilities is roughly 0.8433 and the other one is 0.9977, much higher. Why are these probabilities so different? Well, the mean length of 5 tends to average out any individual extreme values, resulting in a smaller standard deviation. And this is reflected in the formula too. If you look at the formula, standard deviation for x bar is the standard deviation for the x distribution divided by the square root of n, so it's going to be smaller. So if somebody gets a very large trout, well, before you get to the x bar distribution, you need to average that trout with 4 other ones, right? So it's a mean length of 5, and that tends to average out the extreme values. So you get a smaller standard deviation. There's a picture in the book on page 322, and you can see these graphs here, and this is the X distribution. The mean is 10.2, standard deviation 1.4, right? So this is a number line, this is the length of the trout. And the X distribution has this bell-shaped curve. You can see the spread that it has here. And if you compare that to the X bar distribution, this is pointier, right? So where this one between 8 and 12, you get, 84, roughly 84% of the curve, but there's still this out here and here. Well, the X bar distribution has the same mean, but the standard deviation is smaller, so it squeezes it together more, right? So that between 8 and 12, you get almost everything. Because remember, the area under these curves is the same, but this one between 8 and 12 only gets 84% of it, where this one gets almost all of it between 8 and 12. There's just not much left out here, right? So this is the X distribution, X bar distribution. This is a distribution of samples, the means of those samples. X bar is a mean, right? It's the mean of all those samples, and although they have the same mean, of 10.2, the standard deviation here is less, so it's much skinnier. So now we come to a question: what happens if we don't have information about the shape of the original distribution? Well, in that case, what we do is we use the Central Limit Theorem. So there are a lot of math subjects that have fundamental theorems. Like there's a fundamental theorem of algebra, fundamental theorem of calculus. There's even a fundamental theorem of arithmetic. There's no theorem with that name in statistics, but this one would, if there were a name of the fundamental theorem of statistics, it would probably be this one, the Central Limit Theorem. Central Limit Theorem is probably the most important theorem in statistics. It's definitely one of them for sure. So, Central Limit Theorem, and this is how important it is, it even has its own acronym, CLT. Be careful not to confuse that with TLC, which was a hip-hop group from the 90s. T-Boz was the cutest one, by the way. But just so there's no confusion, this is not TLC, it's CLT, the Central Limit Theorem. So for this one, if we let x be a random variable with any distribution, and that's kind of the key, any distribution at all, it's not like Theorem 6.1 that says, well, we are starting with a normal distribution. This one's saying x is a random variable with any distribution at all. Maybe normal, maybe not normal, maybe we don't know what it is. But it has a mean of mu and a standard deviation of sigma. Then the sample mean x bar, based on a random sample size n, will have a distribution that approaches the distribution of a normal random variable with mean mu and standard deviation, same as before, sigma divided by the square root of n, as n increases without limit. So what that means is this: the sample mean will be approximately normally distributed for large sample sizes regardless of the distribution from which we are sampling. So here's the importance of this. So the sample mean x bar will be approximately normally distributed for large sample sizes regardless of the distribution from which we are sampling. So let's say you have this weird distribution here. Definitely not normal. We can't use any of the things that we learned in chapter 6 on this, right? We can't use normal CDF, inverse norms, z-scores, any of that, and any of the other things that work with a normal distribution. But the central limit theorem says if we take samples from this distribution that are large enough, and we plot all the samples here on this number line, what we're going to end up getting is that the x bar distribution will be normal. So here's this weird x distribution, and here's the x bar distribution that we get from that. So What's important about this theorem is that if we're trying to study this distribution, as long as the sample size is large enough, we'll talk about that, what makes it large enough, then if we take samples from here and plot them, it doesn't seem like it would work, but it does. We plot samples from here, and we line up the samples, we get this nice bell-shaped curve. So then we can use all of our Chapter 6, all the tools that we learned and many more on this, and then infer back to the X distribution. So the central limit theorem is really huge. That allows us to study these weird distributions or these unknown distributions and get a lot of information about them by studying the sampling distribution that comes from them. So what exactly does the central limit theorem tell us? Well, it gives us information about the characteristics of the sampling distribution, right, of the X bar sampling distribution. So we're taking means of these samples based on all samples of size n. When n is sufficiently large, and here's our magic number, 30 or more. So in that case, the central limit theorem tells us that, and we have these things here, these three things it tells us. Now, 30, there are exceptions to this, but in most cases that you're going to run into, 30 will work. So in all the cases that we run into in here, 30 will be just fine. A lot of times you need a lot less than 30, but 30 was a line that was found empirically just by studying these things. And most researchers agreed that if you get to about 30, in most cases, you're going to be just fine. So that's the number that we're going to use. So when n is 30 or more, then the central limit theorem tells us that the X bar distribution is approximately normal. Now remember, the difference between the central limit theorem and that theorem 6.1 is the central limit theorem says that we're sampling from this distribution that doesn't have to be normal, right? Or it could even be not normal. So that's the difference. And as long as we have a sample size of 30 or more, then the X bar distribution will be normal. The mean of the X bar distribution is the same as the mean of the X distribution, right? The original X distribution. So we've seen this before. So these are the same. And then the standard deviation of the X bar distribution, also known as the, who remembers that? See, it rhymes with standard error. Oh, that's terrible. Standard error. I couldn't think of anything. It rhymes with those. Standard error. Okay, so the standard deviation of the X bar distribution, also known as the standard error. Again, you'll see this on computer printouts for statistical software. You see it mentioned in the book occasionally. I don't usually say it. I just say the standard deviation of the X bar distribution. But the standard error is this, same as we saw before, where sigma is the standard deviation of the original distribution. And then there's a little note here, when the sample size n is greater than or equal to 30, again, this is our magic number, greater than or equal to 30, we can convert the X bar distribution to the standard normal Z distribution, right? Z-scores, standard normal, so Z distribution or Z-scores, using these which we've seen before. I mean, we saw these in theorem 6.1. The central limit theorem is just less restrictive. It says it works for anything as long as we hit this magic number in our sample size. And for the Z-scores, again, I say the same thing as before because this gives us all kinds of trouble. Be careful with the order of operations. And what is the other thing? Make sure you divide. Make sure you divide here. And, okay, yeah, that's good. So let's try, I want us to try, before we do this one, let's try something else. Let's try to squeeze in here. Let's try to squeeze in number 6. Number 6 on page 328. Let's try to take a look at that one first. Okay, so we've got number 6 here. I'm pretty convinced that I'm unable to make circles on this tablet, on the whiteboard. I'm not bad, honestly, making circles on the whiteboard, but these are terrible. So we've got this X distribution in this kind of a circle. So just think of this as a bunch of numbers. We don't really know much about it, but we know that the mean is 20, the standard deviation is 3. Now notice in number 6, it doesn't tell us that X is normal. We don't know that it's normal, so it may not be normal. We just know that the mean is 20, standard deviation is 3, and we're going to take random samples of size 36. So think of this being just a giant pile of numbers, thousands of numbers, and I'm going to randomly take samples out of here. Another horrible circle, n equals 36, so we get some kind of sample, x bar equals something or other. We take another sample, size 36, right? So our sample is of 36 numbers, and we take the mean of those 36 numbers, and we just keep doing this. Samples of size 36, we take the mean of the samples. All right, so part A says, describe the x bar distribution and compute the mean and standard deviation of the distribution. Okay, well, the x bar distribution, I'm going to say this, it will be normal. How can I say it will be normal when I don't know about the x distribution? Well, the reason I can say that is because the sample size, right? The sample size is 36. So the reason I can say this will be normal is because n equals 36, which is greater than or equal to 30, and that's because of the Central Limit Theorem, right? So I know the x-bar distribution will be normal. If they had told us that the x distribution was normal, then it doesn't even matter what the sample size is, right? If we're sampling from a normal distribution, we're going to get a normal distribution. But here they didn't tell us that. So if this would have said n equals 26, then I wouldn't be able to say this. And that would be considered a small sample, which is not something we even cover in this book. So for small samples, we have to do different statistics. So for us, as soon as we hit that magic number of 30, we're okay. Even though we don't know if this is normal, because they don't tell us, this will be normal because our sample size is 36, and that's above the magic number of 30. Okay, so that'll be normal. Then it says compute the mean and the standard deviation. Well, the mean of this x-bar distribution is the same as the mean of the x distribution, so we know that's 20. We don't even need to do anything, right? They're going to be the same because our sample size is 30 or more. So that's the same. Then we've got a formula here. The standard deviation of the x-bar distribution is the standard deviation of the original distribution divided by the square root of n. So the standard deviation of this x distribution is 3 divided by the square root of n, which is the square root of 36. Okay, I know you guys would never leave an answer like that, right? Think about this. Let's say it's date night, and you go out, math seminar, go to math seminar, go out to eat, date's going great, everything's awesome, and then your date's like, hey, would you like to come on in and work on some statistics? And you're like, I sure would. So you go up there, working together on your homework, and then your date says, here's my answer, that's good enough for me. Want to make out now? And you're like, no, thank you. I think I'm going to go home. Right? Who could do this? You can't go with somebody who leaves an answer like that. The square root of 36 is 6. You wouldn't even be happy with somebody who left an answer like that, right? It'd have to be either 1/2 or 0.5. Okay. So hopefully that will never happen to you. So part B says, Find the z-value corresponding to x bar equals 19. X bar equals 19. We want to find the z-value corresponding to that. Well, since this is x bar and not x, we have our new z-score formula. I'm going to do what I always do, just to make sure we're careful here. So we just plug in the values. So we've got 19 minus 20, and sigma is 3 divided by the square root of 36 again. So we just did this math right here, right? We know that's going to be 0.5 down here, but just to go through it again, we'll say 19 minus 20, that's negative 1. So on the bottom, we've got 3 over 6, which is negative 1 over 1/2. And we actually don't ever want to leave a fraction like this. This is a complex fraction, or a fraction inside of a fraction. So this will be a little review from the good old days in elementary school. So this really, couldn't you really look at this and say this is negative 1 divided by 1/2? Right, so you could think of it as negative 1 divided by 1/2. Because you can always read a fraction bar is divided by. And then you guys would have learned a long time ago, we never divide fractions, but instead we multiply by the reciprocal. So this is really equal to negative 1 times the reciprocal of 1/2, which is 2 over 1, which is just negative 1 times 2, which is just negative 2. Whoops, oh boy, what just happened? It's just negative 2. Where are we? Here we go. All right, which is negative 2. So the z-score corresponding to x bar equals 19 is negative 2. And then for part C, it says, find the probability that x bar is less than 19. So the probability that x bar is less than 19. So what we do is we always convert it to z-scores, which we just did. Right, so we just converted x bar equals 19 to a z-score. So the probability that x bar is less than 19 is the same as the probability that z is less than negative 2. And then this is going to be a normal CDF. So remember what this is saying. This is a z-score, right? So as soon as it's standardized, it's just basically this. Here we go with a standard normal. 1, 2, 3, negative 1, negative 2, negative 3. And we are, I don't know why this is this. Okay, let's try this again. We are right here. Right, so we're looking for the probability that z is less than negative 2. Remember, I could have wrote z less than or equal to negative 2. It's the same, right? With a continuous distribution, that additional point adds nothing to it because the point, remember, is infinitely small. So anyway, you could put a negative here. So to answer this question, I need all of this area here. In normal CDF, we always start lower bound, comma, upper bound. The lower bound here is going to be negative infinity, or as far as our calculator is concerned, negative 10. And the upper bound would be negative 2. Right? It's always the number on the left and then the number on the right on the number line, right? Lower bound, upper bound. And it looks like if we do this, we're going to get about 0.0228. Pretty small. 0.0228. So part D says interpretation. Would it be unusual for a random sample size 36 from the X distribution to have a sample mean less than 19? Well, I guess it depends on how you interpret unusual. Most people probably say yes, because looking at this thing, it means you've got about a 2.28% chance, right? Or maybe around a 2.3%. So I guess it kind of depends on what you think is unusual. The author says yes. And we'll actually talk about this in hypothesis testing. Some people think this is unusual. in research, some people will say if you get something that's got a 5% chance of occurring, it's unusual. Others say, no, I'm going to use 1%. So you can make an argument either way. But according to our author says yes. But again, that one's a little, just depends on your opinion. This answer is right. This is the right answer. And most people would say, yeah, there's only a 2.3% chance of that happening. It's kind of unusual. So we could say yes. And why? To explain, you could just say, well, only 2.3% of all such samples have means less than 19. So it's kind of unusual, right? Only 2.3% of them have that. So, okay, so I just wanted to see that one before we did one that was a little bit more involved. So that was problem number 6. So let's take a look at page 329, number 14. And it talks about the heights of 18-year-old men. And it says the heights are approximately normally distributed. So we've got data that are going to follow the normal distribution. It says the mean is 68 inches and the standard deviation is 3 inches. And then there's a few questions here. This is actually a really good question because it's going to tell us the difference between sampling one person and sampling a mean of more than one. So part A says, what is the probability that an 18-year-old man selected at random is between 67 and 69 inches tall? So I'm going to write part of this, so I'm going to write it up until the important part. So the important part is here. What is the probability that an 18-year-old man, N is 1, right? That's just one person. This is one person. So we're going to use our old, to convert to a z-score, we use our old method, our old formula from section 6.3, because we're just talking about one person. So when we convert to a z-score, we're going to use this. We've got this one data point. It says, what is the probability that an 18-year-old man selected at random is between 67 and 69 inches tall? So they're basically saying this. What is the probability? Right here, right? This is the one that we're looking for. So we're going to convert to z-scores, of course. So we've got z equals, and I'll do the 67 first. So we can get negative 1/3. And then for the other one, looks very similar. Positive 1/3. So basically we really want to know what's the probability that negative 1/3 is less than z, which is less than positive 1/3. So again, this one being below the mean, less than the mean, it's going to be negative. And this one being above the mean is going to be a positive z-score. So this is actually a good one to see how the calculator handles differences. So if I do this on the calculator, if I go normal CDF, and let's say I use, just going to plug in, like if I go negative 1/3, comma, then 1/3 like this. So if I do that, the calculator is going to interpret that as a whole bunch of 3s. So we've got 4, 5, 6, 7, 8, 9, 10, something like this. And there's probably a couple extra ones in memory. But what if I do this? What if I just say, well, it's roughly 0.33 to 0.33, right? Like we know this 1/3 is just 0.3 repeating forever, right? Just keeps on going. So if you round to 2 decimal places, which is fine, I just want you to see the difference. On the calculator, it's going to do the second one as 0.33, and then every one of these is 0. So if we plug in the fraction like this, we're going to get one answer. If you plug in the fraction, or if we do an approximation to the fraction like this, we're going to get a different answer. So I just want you to be aware of that. This one gives us 0.2611. This one, 0.2586. So they're far enough apart where if you're not really expecting it, you might say, oh, something's wrong. But it's really not. I mean, this is more accurate because these are all zeros. But when we grade these in class, I accept either one of these. Now, grading on software, if you're using WebAssign or something, we'll have to see what happens. But if anybody gets marked wrong on WebAssign, if you're doing it correctly, just let me know, of course. And I'll mark it right. And if you were to look in the back of the book would probably give this answer. So just be aware there's going to be some variation here, just depending on how you enter these. So even though this one doesn't look all that close, if you get this and the book has this, you're fine, right? You're just using a calculator that has more significant digits. But okay, so that part A is talking about the probability that one person. So then part B says, if a random sample of 9 18-year-old men is selected, what is the probability that the mean height is between 67 and 69 inches? Okay, so here, for this one person, there's roughly a 26% chance, right? I'm just going to write this over here just so I have something to work with. So about a 26% chance. Okay, so then part B, I'm going to, again, write until we get to the important part. So this one says, if a random sample of 9 18-year-old men is selected, what is the probability that the mean height x bar is between 67 and 69 inches? But the important part here is 9, right? There's not 1, there's 9. So what we need is our new z-score, x bar minus mu, sigma divided by the square root of n. Because we don't have one individual data point like we did up here. Here we have a sample of 9, so we need x bar. So that's what we have to be aware of. If we're talking about the probability of one thing, this is like the trout problem too, so you've got two examples of this now to look at. One thing, we use our old z-score. A sample of 9, we need our new z-score. So it's asking us the same question basically. It's saying what is the probability of 67, but not x. This time it's x bar, right? The mean of 9. But it's the same sort of question. So we rewrite it as a z-score. So I'm going to rewrite this. We want z-scores here. And we need our new formula. So using this formula here, and I'll do for 67 first. So we go 67 minus the mean of 68. And then the standard deviation is 3 divided by the square root of 9. Kind of convenient how they did that, isn't it? The square root of 9. So if we do this, we get -1, and on top we get, or on the bottom we get 3 divided by the square root of 9. Well, the square root of 9 is 3. What's 3 divided by 3? That's just 1. -1 divided by 1 is just -1, right? So in the other z-score, very similar to this one. So we get 1 over 1, which is just 1. Okay, now everybody should be able to get this one right. All right, everybody should get this one right. What's the probability that the z-score would be between -1 and 1? You don't even need your calculator on this one. This is one of our magic numbers from section 6.1. So if you use your calculator, you'll get about 0.6827, but just on your own, you should be able to get 0.68, remember? That changes to -2 and 2, 0.94, 0.95, -3 and 3, 0.997. So the calculator will say 0.6827, but we kind of already knew that one. So we just have to do, just have to be aware of if we're dealing with one data point or a mean of more than one. Okay, but other than that, they're very similar. So I skipped the last part here about the normal CDF, right? But it's because it's one that we know. But you could type in normal CDF, -1 to 1. I guess just to make it official, let me do that. Normal CDF, -1 to 1. And then it should give you the 0.6827. So usually after this section in class, I show this YouTube video. And it's by this, I don't know if it's a person. Well, I know it's a person who puts these videos out called JB Statistics. This one's called Introduction to the Central Limit Theorem. It's about 13 minutes long. But it's a really good video because he uses computer graphics to show these weird distributions, and then he takes samples from them and comes up with the sampling distributions, and it's the best one I've seen. Unfortunately, the software that I'm using does not allow us to record a YouTube video in the file itself, so we're going to have to do this one the old-fashioned way. I'm going to show you a video from JB Statistics called Introduction to the Central Limit Theorem. The actual video is about 13 minutes long, but we just need to watch the first 8 minutes. And right at the end of our video, it gets into a little bit technical details that we don't really need, but it's just the last few seconds. So this JB Statistics makes some pretty good videos. So you could just go to YouTube and search for just JB Statistics, and he's got quite a few of them out there. They're pretty good.
Let's talk about the Central Limit Theorem, an extremely important concept in statistics. The gist of the Central Limit Theorem is that the sample mean will be approximately normally distributed for large sample sizes regardless of the distribution from which we are sampling. And I'm going to illustrate this using simulation in a little bit. First, let's recall a few characteristics of the sampling distribution of the sample mean. Suppose we are sampling from a population with mean mu and standard deviation sigma. Let x bar be a random variable representing the sample mean of n independently drawn observations from this distribution. We have previously learned that the mean of the sampling distribution of the sample mean is equal to the population mean. The mean of the sampling distribution of the sample mean is equal to the mean of the population from which we are sampling. We've also learned that the standard deviation of the sampling distribution of x bar is equal to sigma over the square root of n. As previously discussed, if the population is normally distributed, then the sample mean x bar is also normally distributed. But what if the population is not normal? Well, the Central Limit Theorem addresses this question. The distribution of the sample mean tends toward the normal distribution as the sample size increases, regardless of the distribution from which we are sampling. Let's illustrate this through simulation. Here's an exponential distribution, which is most definitely not normal. And what I'm going to do is I'm going to draw a sample of 2 observations. So n is 2. I'm going to draw 2 independent values from this distribution and get the mean. And I'm going to do that again, and again, and again, 1,000,000 times. And so we're going to get 1,000,000 sample means where n is equal to 2. One thing to note right off the bat is that I'm allowing the y-axis scaling and the x-axis scaling to change. What we're interested in here is the shape of the distribution. The gray histogram here is a histogram of those 1,000,000 sample means where n is equal to 2. And this is going to be approximately the sampling distribution of x bar in this scenario. In this particular spot, we can mathematically work out the exact sampling distribution, but here I've done it through simulation. We can see that this distribution retains some of the original distribution here. We've got some right skewness. It's most definitely not normal. Here, with this white line, I've plotted in, superimposed a normal curve with the appropriate mean and variance. And we can see here that when n is 2, the sampling distribution of the sample mean is not normal. But let's see what happens when I increase the sample size. Here again, I've drawn 1,000,000 samples. This time, the sample size in each one of those samples is 4. And I've plotted out those 1,000,000 sample means in a histogram. And that is approximately the sampling distribution of x bar when n is 4. Here again, we still have some of that skewness. And it's not quite normal, but it's getting there. Still quite a bit different from this superimposed normal curve, though. When n is 10, we're getting a little bit closer, but we can still see some of that skewness. When n is 20, we're getting closer still. And when n is 50, this histogram of sample means, which is approximately the sampling distribution of x bar when n is 50 here, is pretty close to that superimposed normal curve. So for a sample size of 50, the sampling distribution of x bar is pretty close to normal. And we'd see if I did this for larger and larger sample sizes, it would be getting more and more normally distributed. It would look better and better and closer to that superimposed normal curve. What I was illustrating there is that when we are sampling from non-normal populations, the distribution of the sample mean tends toward the normal distribution as the sample size increases. As a very rough guideline, the sample mean can be considered to be approximately normally distributed if the sample size is at least 30, if our n is at least 30. Again, this is a very rough guideline. We can easily construct scenarios in which a sample size of 100 trillion is not nearly enough to give us approximate normality. But in most practical situations, when our sample size starts getting up beyond 30, the distribution of the sample mean will be approximately normal. Let's do another simulation for a different distribution. This one's a bit of a weird mixture type of distribution. So the same scenario as the last time. I'm going to randomly and independently draw 2 observations from this distribution, calculate the sample mean, draw another 2 observations, calculate the sample mean, and do that 1,000,000 times and plot out a histogram. Here, the gray histogram is approximately the sampling distribution of x bar when n is equal to 2. And I've superimposed a normal curve again. And obviously this distribution is not quite normal. Let's increase the sample size and see what happens. Note that in this series of plots, I'm keeping the scaling on the x-axis the same and letting the y-axis scaling change from plot to plot. Here I've done this 1,000,000 times, sampled from the original distribution 1,000,000 times for a sample size of 4, and plotted out the 1,000,000 resulting sample means in the histogram. So the gray histogram is approximately the sampling distribution of x bar when n is equal to 4. And I've superimposed the normal curve with the appropriate mean and variance. And we can see here that the sampling distribution of x bar is actually quite close to normal. And we'll see that when we let the sample size increase, it's going to get closer and closer and closer to that superimposed normal curve. Here, when n is 10, the sampling distribution of x bar looks quite normal. When n is 20, it's even closer to that normal curve. And when n is 50, it's looking very normal. And the sampling distribution of x bar would get closer and closer and closer to a normal distribution as the sample size increases. Why is this important? Well, the Central Limit Theorem tells us that many statistics have distributions that are approximately normal for large sample sizes, even when we are sampling from a distribution that is not normal. And this means that we can often use well-developed statistical inference procedures and probability calculations that are based on a normal distribution, even if we are sampling from a population that is not normal, provided we have a large sample size. A little more formally, the central limit theorem tells us that our usual z-score value here involving the sample mean, that tends in distribution to the standard normal distribution as the sample size tends to inflate.
So don't worry about that last frame, but otherwise it's a good video. So hopefully that will put you in good shape to handle the 6.5 homework. So give it a shot, and of course, you know what to do if you have any questions. Just send me an email or stop by for the Zoom office hours. So have a great day, and I will talk to you guys soon.